Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to be talking about a phenomenon you've probably encountered on a daily basis since you were young kids, and this is the idea of gas pressure. So this is what underlies either the measurement on a propane tank or whenever a meteorologist talks about a low versus high pressure system coming in. What are they actually talking about? So as a result, it turns out that when I'm talking about macroscopic or measurable quantities of gas, one of the most important ones is going to be pressure. So first we have to talk about what pressure is from a physics perspective. So pressure is going to simply be the force applied to a given area. So if you push on something, you're applying a certain force, and if you put it over a narrower area, you're putting more pressure on that single point. Well, it turns out you constantly have infinite forces bombarding you from every direction all the time. Those are all those fast-moving gas molecules hitting you at high speeds. However, since there isn't a lot of mass behind it, they tend to have a relatively lower force. And this means that we tend not to think a lot about the pressure applied by gases. However, when we're talking about chemical systems, you can start measuring a lot of things about the gas inside of a system by simply looking at how much force it applies to a known area. So if you're looking at an isolated gas sample, one of the easiest ways to try and measure its pressure is by putting it in a piston. So a piston is pretty much just a cylinder in which you put in the gas with a movable barrier. So what's going to end up happening is as the gas has more pressure, the piston will move up. If the gas has less pressure, it will move down. So by measuring exactly how much force it applies to that piston, you can figure, which contains a known area, you can find exactly how much pressure the gas has. And one of the easiest ways you can do this is by making that force applied by simply putting a mass on top of the piston. Now, one of the cool features of when you do this is that if you know the mass, you're going to get the force based on the acceleration of that mass. You say that mass isn't accelerating at all, but this is where that pesky idea of gravity comes in, because gravity puts a constant acceleration on any falling object. So in this case, the acceleration of that stationary mass would be 9.8 meters per second. So you can convert that mass into a force with units of kilograms per meters per second squared. So this specific unit is also known as a Newton. I won't use it too much, but it's important to know what we're talking about when we introduce this idea of newtons. So again, pressure isn't force alone. It's also based on the amount of area that force is being applied on. So if I put a mass on top of that piston, I also need to know how big the area is. So that area would be reported in meters squared. And it turns out if you have newtons per meter squared, this is a unit known as a Pascal. So this is P, big P, little a. So this is one of our common units of pressure. Newtons per meter squared gives us Pascal. Now, this works pretty well if I'm looking at a small gas sample. However, if I try and invert this around and try and figure out things like the pressure of a bigger amount of gas, like, the atmosphere, doesn't work quite so well. So we tend to use a much kind of older, but I think cooler device. And this is the barometer. So a barometer works by having a pool of liquid, which you're going to have atmospheric pressure pushing down on the liquid. Now, normally the liquid's going to say, I don't care. But one of the cool things you can do is if you put a tube full of vacuum inside of this liquid, well, now there's no atmospheric pressure coming down on this part of the liquid. There's pressure coming down on that part of the liquid. So the liquid will rise until the point at which it puts enough pressure on itself to stop the more liquid being lifted up into the vacuum. So this is one of the ways you can often, say, pick up a little bit of liquid into, say, a straw. If you put your thumb over the end, you create a minor vacuum, which some liquid will come up into. Now, since it's a very bad vacuum, not much moves in. Now, if you do this with a perfect vacuum, you can actually figure out the atmospheric pressure based on the height to which the liquid is lifted. And it turns out that this pressure will be equivalent to, again, the force times the area, which can be related to the height to which the liquid is lifted, that gravitational constant, so again, that 9.8 meters per second squared, and the density of the liquid. Now, it turns out that to do this as well as possible, you need a liquid that isn't going to stick too much to the glass or doesn't have too many cohesive forces like water or is too chaotic. So you want something that is very well behaved as a liquid. It turns out one of the best liquids to do this with is mercury. Yep, there's a reason you don't tend to see many traditional mercury barometers anymore, because the whole premise involves having an open pool of mercury sitting around. However, you can mimic this with modern electronics and with other alcohol-based liquids. However, this was, again, originally designed for mercury, which has a nice constant density. And as a result, one of our major units of pressure is still based on this idea, because it turns out that at atmospheric pressure, you're going to tend to raise this mercury to a very constant height. So we list this unit of pressure as millimeters of mercury, so the height to which the mercury is lifted. So at millimeters of mercury is often also expressed as torr. So this is named after Evangelista Torricelli, who was a student of Galileo and was the inventor of the barometer and invented it back in the 16th century, giving his name to this unit of pressure. So as you may notice, one of the pesky parts about pressure is that we have a lot of different units. So let's go ahead and go over some of the major units of pressure. So the one you may be the most familiar with is this idea of the atmosphere. So this is atmospheric pressure at essentially sea level. So this is kind of average. Now, if you're going to turn this into millimeters of mercury, turns out 1 atmosphere is about equivalent to lifting a column of mercury to 760 millimeters, so almost a full meter. So that also means that 1 atmosphere is equal to 760 torr. However, if you like working with pistons, it turns out 1 atmosphere is equivalent to over 100,000 pascals. So as a result, instead of referencing things in terms of pascals, we often use kilopascals. However, because Pascal is a natural SI unit, but it's far too small, the traditional SI unit is something called the bar. So 1 bar is going to be equivalent to 101,000 pascals, which means that 1 atmosphere is equivalent to 1.01 bar. So this is a much more natural conversion, and a lot of people convert these willy-nilly. However, watch out, they do have a 1% difference in their units. However, if you're working with something of very low pressures, it's a little bit more convenient to sometimes use millibar instead, which again is the classic SI conversion. There's 1,000 millibar in a bar. So be very comfortable with all these units of pressure. Various resources tend to use various pressures. So atmospheric chemists like to use atmospheres, millimeters of mercury, and torr. Physicists and chemists, physicists tend to like using pascals and bar, and chemists, well, we're a varied lot and we'll use any of them. And pretty much any biologist will use whatever their advisor told them to use. So they also tend to use any of these numbers of pressures. So be comfortable and be aware that all of these units are out there. So now that we have a good understanding of pressure, next time we're going to look at how pressure will vary as we start changing things like volume, temperature, and, well, the amount of substance present. Until then, take care.